Uh, Good Friday to everybody. This is Brent with Lykins Motorsports, and over the past 3 or 4 weeks, I have tried to find some industry guys to come on the channel and talk about different things. A couple weeks ago, we had Jay Brown with FE Power to discuss his new cylinder head package for the Ford FE. And this week, we have Mr. Keith Jones from Total Seal Piston Rings, and I thought it would be beneficial for him to come on. And I have a list of questions to ask him, just different things that you guys probably would benefit from to hear as you are building your own engines at home, just some tips and tricks and some new technology. So, without further ado, we'll introduce Mr. Keith. Uh, so, how long have you been in the motorsports industry, Keith?
Pretty much all my life. I'm from the suburbs of Chicago originally. Uh, Grew up, just say, like a lot of us, it's in my DNA. Grew up around it. The old man was a gearhead. Uh, had the honor of hanging out with, Arnie the Farmer Beswick for those older Pontiac lovers like me. Mr. Pontiac, great guy, still alive and still as sharp as a tack. That man knows. I mean, I believe Arnie's in his 90s and still as sharp as ever. Uh, and so I grew up around the whole thing. So I've been kind of doing this all of my life. And like I said, I can't imagine being in any other industry. Working at a Home Depot may be great for some people, but I don't know if I could ever do it.
Yeah, I hear you. And how long have you worked for Total Seal?
A little over 25 years.
25 years. Yeah, well, that's a good long history with a company. I've been using Total Seal for, well, I've been building engines for about 20 years. And my very first engine that I ever put together was a stroked Windsor, and it had Total Seal rings in it. So it's good to have companies like Total Seal that specialize in one thing only. There are companies that make piston rings, but they also do other things. It's good to have businesses that focus 100% on piston ring development and technology. So, do you have any cars or race cars yourself?
Not currently. I've had many, many, many over the years. My most recent project was a 72 Pontiac Ventura. So we'll say like a Nova, but not a Nova. Did kind of I'll call it a resto mod kind of a thing. Bigger tires, wheels, brakes, etc. But that's gone down the road. So any of you that have an interesting project that you want to unload, you might reach out to me. You never know, might spike my interest. But I've raced, since I was in my teens, bracket racing out at Speed World, and eventually worked my way into a super comp dragster that I ran for years, and would just say different motorcycles and cars, and kind of gotten the resto bug on some old motorcycles lately, and would just say anything that piques my interest. It's easily diverted and easily routed to other things, and that's why it takes so long for me to get anything done.
I have a soft spot for Pontiacs. I'm mainly a Ford guy, but the Pontiac guys are, I don't know. It's just they're not. I'm sure if any Chevrolet guys are watching, they're going to skewer me for this. But to me, Chevrolet motors are belly button motors. Everybody's got one. They're all the same. Ford kind of lean in that direction, but the Mopar guys and the Pontiac guys, it's a smaller bunch of guys and smaller knit groups, and you don't see as many of them. So I'm kind of drawn to those sorts of engine families, and I've built a few Pontiacs, but mainly Ford stuff. But they had some beautiful cars back in the day. Um,
Exactly.
yeah,
Yeah.
even the what was the Pontiac copy of or the version of the Chevelle? I guess the Tempest, right?
Well, that would have been either Le Mans or the GTO as far as the Chevelle, but you had, in the early day, the Tempest, which, it evolved, the A-body GMs, and then, of course, Camaro Firebird. I love them all. I just think the Pontiac styling through, and again, nothing against Chevrolet. I'm a GM guy, but I appreciate Fords. I've got, one of my best friends is a big Ford FE guy, and I appreciate every brand out there. I mean, who turned down a 70 Hemi Cuda? Come on. Who turned down a 67 Mustang Fastback? I think one of the prettiest cars ever made. I mean, come on. But at the same time, brother, I got to tell you, 61 Ventura, gotta love the lines, But you were talking about the engine swap thing, and one of the things, and the GM guys are going to kill me for this. Stop putting LSs in everything. Good God. I saw an absolutely beautiful 67 Grand Prix. Stunning car, roadster shop car, beautiful. I mean, this has got to be well into six figures. Stunning. You get to the engine bay and it's like, NLS, what are you doing?
Exactly. I share that same sentiment. Yeah, for sure. Or what's worse is seeing a Mustang with an LS engine in it. I mean, that's uh, that's just bad all the way around. That's all kinds of
Well,
not
there is
good.
that contingent of folks out there that say built Ford tough with Chevy stuff. So, I'm not one of them. Ford goes in your Ford, Chevy goes in your Chevy. But, kind of like you said, I love seeing, again, the last thing in the world I want to see is a 32 Ford Roadster with a small block Chevy. Come on, guys, put an old nailhead in it, put an old Cadillac in it, put something cool in it, put something interesting in it. I've speaking to a gentleman earlier last week, I'd love to have like an R07 Chevy Cup motor, not because of the power, but just because of the weird factor to put that in something and somebody looking under the hood going, what the heck is that? What's an R07?
Yeah,
I love different, so that's the fun thing. And it's kind of, I grew up in a Pontiac household. My dad worked for Pontiac dealerships, most of his life. And though he was a Dodge guy towards the end of his days, he loved his Mopars, but grew up around Pontiac, so it's just the Pontiac things in my blood.
very good. So, in your 25 years of working for Total Seal, what are some of the big things that stand out in the back of your mind as just big developments that came out as far as technology and piston rings and that sort of thing?
Well, stuff, and a lot of people know this stuff, but we'll kind of in the early days. I started with Total Seal in '97. Matt Hartford started a year after me, and we had a gentleman, Ed Law, who's since moved on to other things. Kevin's here, August. Lake Speed's with us now, and Scott Deal, who's also with Lake and driven for years. We've got I'll call it a great cast of characters around here, and we're always, what's the next thing? What can we do? We're never comfortable just sitting here going, this, hey, this is as good as it gets. But, and the honest truth, if you'd have asked me in 1999 or 2000, ring sizes, coatings, materials, and the whole package of where we are today, would we be here? I'd have said, not in a million years. Can we make a ring that's 0.5 millimeter, 20 thousandths of an inch thick? I mean, come on, folks, that's thinner than an oil ring rail, and yet have it hold up for thousands of race miles. I'd have told you you're sick in the head, but here we are. So the bottom line, material technologies have advanced so much, coating technologies have advanced so much, manufacturing technologies, how we make the rings, have completely changed. And this has all been, I'll call it, I hate to say the word driven by, but, by the behest of the race teams. Because nobody, when was the last time, for all the people out there that have gone to, a PRI or a SEMA, when was the last time you walked up to anybody and said, hey, what's not new? Everybody wants new. What's new? And nobody ever walks up and says, hey, could you help me knock 30 horsepower out of my junk? Because, it just makes too much power. Even if they've got too much power, we always want more. So we're always being pushed by the teams to find the next thing. What's the next thing? And most recently, that is material and coating technologies. Very fortunately, Lake's been working with the guys at Southwest Research Institute, and I got to tell you, folks, we've got some coating stuff coming down the pipeline. I can't talk about it right now, but it's a game changer. And fortunately, between their efforts, our efforts, his efforts, it is a group team thing. We've got some real interesting things, but the big drive has been thinner, and that kind of covers a couple of the questions here. But being able to produce a piston ring that's thinner, that will survive the environment, that will give us thousands and thousands of miles. I mean, think about what we have for an engine today compared to even the late '90s. I mean, let's go to a small block Chevy. I mean, you had 564s, 564s, 3/16 rings. The compression rings made 6-7 pounds of force. The oil ring was 20 pounds plus. Uh, and we were going 100,000 miles. I mean, you'll remember, about 80,000, 100,000, you're saving your money to get a timing chain and gears put in it because the plastic was going sideways. And man, we're going to be putting a motor in pretty soon. Today, I mean, 250,000 miles is not unheard of. And that again is because of, oil technologies are better, but a big part of it is, cylinder block the technology is better. They're harder, they're stronger. We're making them out of better material. But one of the big ones is the ring technology. We're simply building it out of better materials, better coatings, We can hold tighter tolerance. It's an entire evolution of the part, from how we made the parts to, again, what we used to make the parts out of.
Yeah, when I first started building about 20 years ago, it seemed like the popular ring was the 16th, 16th, 3/16 stuff. And
Mhm.
then when the metric stuff came in, it was like a game changer as far as wear, as horsepower, as all of that. And still today, it is very difficult for me to talk my customers into a metric ring pack because they think, oh, it's thin, it's flimsy, it won't seal, it won't wear as long as the older rings do. Um, would you mind just saying a few things about that? Why the metric ring
Oh,
packs do so well?
yeah, 100%. I mean, that's what you just mentioned is an every single day conversation for myself and all the other guys. This is, the practices and the things that we do in this industry are what I want to refer to as generational. I'm doing it because that's what my dad told me to do. He's doing it because that's what his dad told him, or mom, whoever it is in your family that got you into this thing, you can blame them for it. But we have this generational information that gets passed down. And, these big, thick rings are what we always ran. And trying to get it through some, we'll say, and I'm one of the older guys. So trying to get it through some of the older guys that, hey, thin is in, that you don't need these big rings because, again, the material technologies are so much better. Back in the old days, all we had to work with was cast iron.
Hmm.
I'm working on a project right now with a customer that's got, 3/32, 3/32, 3/32, and a 4 millimeter 5/32 oil ring in this package. And we've got the engine sealed up really good. He said, man, it seems like it's got a lot of friction. I'm like, no kidding. Look at the tractor rings you got on there. Let's put some thinner stuff on there. This is how it's always been done in these engines. So you had to have big fat rings to do the job. Well, that's not the case today. We've got all kinds of better materials, from cast irons like the old days to ductile irons, hardened ductile irons, stainless steel, carbon steel, tool steel. We've got all kinds of much, much tougher materials that handle a lot more heat. The issue you had with the older parts being out of like gray irons and things like that, they wouldn't handle a lot of temperature. They'll anneal very quickly. So, meaning we're going to take the ring and we're going to collapse the ring. We're going to close the ring down. It's going to lose all its tension and it won't hold up. The other side you had out of the cast irons or the gray irons is they're very brittle. You start putting that type of ring material into a high compression engine, something prone to detonation, nitrous motor, turbo motor. You're going to, you're going to anneal the ring. You're going to lose its tension simply because it won't handle the temperature, but you're also standing a chance of breaking that ring. This simply isn't that tough. With what we have today, this particular ring's a carbon steel ring, not going to happen. Unless for the guy to anneal this ring and take the tension out, this will be the least of your worries. You're going to have
Hmm.
holes in the pistons. You're going to have a whole lot of bad things going on. As far as breaking it, no, I can turn this thing into a knot. It's not going to break. Again, we're back to material technology. So, but it's getting people to open up their mind, open up their thoughts to, hey, maybe the thinner ring will hold up. The materials are completely different. The other thing you've got with the thinner ring, and I'll grab another little sample. I only got a few things laying on here on my desk. I'm somewhat unprepared. Um, and one of the things that really helps with a ring seal, there's a misconception out there that a thicker, bigger, fatter ring is going to help seal up an engine better. And that is absolutely the opposite of what is true. When we talk about rings, we talk about the axial height, the thickness of the groove, 5/64, 1/16, 1 millimeter, 0.43. That's this thickness. But then the other thickness is what we call the radial depth, face to the inside edge, this dimension right here. That's the real key to getting good ring seal. The thinner I can make this dimension, the more flexible, the easier the ring can follow bore distortion. It will move with the cylinder better. And this is, particularly helpful in today's aluminum engines. Aluminum engines move horrible and they're hard to get great ring seal out of. So by being able to reduce this dimension, we not only one, reduce tension, it takes less force to compress the ring down, but we also allow the ring to be more compliant. It wants to follow the bore. Now, one of the things that we've done on our side is we've created a ring that's got little radial slots all around the inside called the total conform. So there's places and classes where we can't do these other types of modifications, but we'll put the slots in the ring to total conform, and that allows the ring to flex and move and follow bore distortion much, much better for those places where you can't necessarily do that ring. And we've actually done it into the very, very thin rings as well. We've always found a reduction in friction and an improvement in ring seal because the ring can simply follow bore distortion. Again, the misconception that, oh, the ring's going to follow that bore. No, it really doesn't want to. So again, we come back to really got to get those cores straight and round. We've got to give it the best, what I call the house is only as good as the foundation. So we want to give it the best possible foundation we can, and to get that, get that as good as we can. But that reduction in the sizes not only reduces mass, it reduces friction. It also improves conformability of the ring.
Very good. So on a lot of the street engines that I do, I use a lot of 1.5 millimeter stuff and a lot of 1 millimeter stuff. Are you seeing a trend to go smaller than that on street engines now?
A little bit, but not a lot. I mean, the 1 mil combo is very, very good combination. It's great. The 1.5's great. The 1.2's, all of those are great. Anything, I mean, again, you've got that shock and awe factor. You've still got the contingent of guys out there. When you say 1/16, they're like, oh my god, that's the thin ring, not by today's standards. There's OE applications out there that have rings under 1 millimeter today, and they're going hundreds of thousands of miles. So about the thinnest I go on a street piece, we have our 0.9, which is a little bit under the 1 mil. It's about 35.4 and thousandths of an inch for those of you using the imperial numbers. And that's been a very good, very durable ring. I've got them in a lot of street stuff. I've got them in drag cars, 410 sprint cars. They hold up very well. One of the key things to remember with the thin ring packages, and I'll touch on this, is the word standard tension. When you hear the word standard tension, we're talking about oil ring tension. And I had mentioned earlier about the 5/64 ring pack, on say a small block Chevy with a 20-pound oil ring. Well, the word standard is an industry standard. So you have to bear this in mind when you're talking about thin ring packs. Okay, a 3/16 oil ring at 4030 bore standard tension is about 20 pounds.
Mm-hmm.
A low tension 3/16 at 4030 bore is about 16 pounds. That's how much force it puts on the oil, on the cylinder, how much ability it has to scrape the oil back down. Now we jump to, I used to right to the 1.5, 1.53 mil. Because I get people that ask me all this, hey, I want a standard oil, I want a standard tension oil. Okay, well, what is standard for a 3 mil at that bore size? About 10 pounds.
Mm-hmm.
So it's half the tension of a 3/16. Same thing with the 2 millimeter package. What's standard for a 2 millimeter at 4030 bore? Well, that's about 8 pounds. So please keep that in mind when you're speccing these packages out of what that oil ring tension is and what it's needed. The street environment is the absolute toughest, worst environment to control. When I deal with a dedicated race application, that engine's got to go out. It's got to drag race, road race, circle track race, whatever it's going to do, and that's it. Street cars, I've got a cruise park throttle. I've got to sit at a stoplight. I've got an engine brake coming down a mountain where I've got a ton of intake manifold vacuum. And that vacuum's always looking to find oil. So, I put that light of an oil ring into a street car, then help it by putting a high volume oil pump in it where I'm flooding everything, loosen up all the bearing clearances, loosen up the rod side clearance, and put an 8-pound oil ring in it. Guess what? It's going to burn oil. This is what it's going to do. So be aware of what standard tension means. We can doctor oil ring tensions up and down about any way I want. So if I get a street guy that calls me and says, hey, I've got a 1 mil, 1 mil, 2 mil package, it's going in my street LS, and it's a 412 stroker, is that 8-pound oil ring going to keep that engine dry? Not a chance. I will make him up a 15-pound 2 millimeter. This is going to do the job. So always be aware of what that word standard tension means and what it means to what you're doing. It makes all the difference.
I wish the guys that are watching would be able to feel um, what it takes to turn like a short block over with some of the older rings and versus the newer rings. Some of the stuff that I do with the 1 millimeter ring packs, it just takes 7 or 8 pound force, pound feet of rotating torque to turn the short block over. So completely different from the 16th inch stuff and the 5/64 stuff where you feel like you got to lean on it, to get it to roll over. But just just a tremendous difference, and all that translates into more horsepower, less friction, good stuff. So I would like to see more guys lean towards these smaller ring packs, and like you say, it's hard to get it into your head that the smaller stuff, is a better ring. But hopefully, as uh, technology improves and the information gets out on the internet, these guys will start to learn those things.
I couldn't agree with you more. One of the phone calls I'll get is from, what I'll call the professional race engine builder. Say a guy that works at a NASCAR shop or is used to building, comp eliminator engines or pro stock, and they're used to packages that, I mean, gosh, the compression rings make under a pound of drag and the oil rings maybe 3 or 4. You can literally turn the rotating assembly over with your hands. No tools required. Grab the crank and just turn it. In some cases, it will continue to keep turning. They're so light, and they'll help out a next door neighbor, or maybe they're, they've got a parent or an uncle or a relative that they're going to restore, that 55 Ford truck with 352 in it, and they put it all together. And like you said, it's got 3/32 rings and a 3/16 oil ring, and they're on the phone here. There's something wrong here, man. I've got to put a pipe on the end of a breaker bar to turn this thing over. It's going to burn the starter out of it. And, they're freaked out. They haven't built anything like you were just talking about in, 20 years. And it's like, no, that's how they were. That's how they are. They'll be just fine. Just let it go. But there's a massive difference. And not only we're talking about, horsepower to the crankshaft, you're talking when we get into, OE type applications. And this is part of, the CAPA thing that the OEs work with, they've got to lower tailpipe emissions, and they've got to increase fuel economy. What's the number one consumer of friction in the engine? The rings. This is the number one piece that eats up the most friction. So everything we can do, so the OEs are driving this technology as well, because they've got to get that CAFA number. The government says, hey, you got to have this many miles per gallon. Tailpipe emissions have to go down here, and you got to do it by 2025. Well, they're going big time after the ring packages and putting surprisingly thin stuff on. I mean, some of these OE engines, you open up, it's like, whoa, that's race car stuff. That's stuff that, 5-6 years ago, you might see in a cup motor. Now it's in OE application stuff.
Mm-hmm.
So getting that friction down not only improves the output of the crank, better fuel consumption, but the one thing a lot of guys don't catch, it also lowers temperature. We've seen significant reductions in water and oil temperature both, simply because we've got a lighter ring pack and it's less drag.
So the different ring materials, could you spend a minute or two on just the different materials and the different facing that we have on the rings and everything, moly faced and even the diamond stuff? Could you spend some time on explaining those?
Sure, we can. Oh, we can spend a lot of time on it. But the bottom line, you've got I'll call it a ladder of materials and a ladder of coatings. So, starting off with the absolute basic stuff, you're going to have gray cast iron. And gray cast iron's been used for, 150 years. And it works reasonably well, handles a reasonable amount of temperature. It wears reasonably well, but just reasonably. If you're going to build, remember the old days, oh yeah, I want to turn it around and just sell it real quick. You put old plain cast iron. They were cheap. You get 30, 50,000 miles out of them. They'll seat up on a sheet of glass, and away you go. So you did that, but that's not what anybody wants. We want it to last. We want it to seal up well. So we need to move into better materials. So the ladder of materials, you've got gray cast iron. Gray cast irons, we've got to look at the heat treat numbers, or where the material's heat treated and what it's going to take to anneal that part and collapse it. So gray cast irons are generally done in the high hundreds, low 1,000 free range. So there's an exposure period of how much temperature over what period of time it's going to take that part to relax itself. So cast iron's on the lowest end of the scale. So moving up as we get into higher cylinder pressure applications, more temperature. Remember, we're going to make more power. We've got to make more heat. This is what we're talking about. PTUs. We've got to get more energy. We've got to put more fuel. We've got to bottom line. We've got to make more heat. Got to have more bang. So as these numbers go up, we've got to go into better and better materials. So the next step up is like a ductile iron. We've all heard of a ductile plasma moly ring. Well, what we're talking about there is we're moving into a ductile iron. It's got a better grain structure. It's more uniform. It will handle more temperature. It heat treats at a higher temperature, so it's going to take a longer exposure to a higher temperature to get it to anneal itself. It's also, because of the grain structure of the material, it's less likely to fracture. So, gray iron, again, if you take any kind of a piece of cast iron, break it, look at it, you're going to see a very porous, very pitted style grain structure. You look at ductiles, it's more like grains of rice. It's a more uniform grain structure. It's much, much more resilient, much tougher. Then moving up that ladder, now we're moving into like stainless steels, into hardened ductile irons. We've got what we call our AP line of ring, which is made from 440B stainless. We also then have a similar iron we call our TNT, which is kind of like the old Hellfire ring, the sealed powder used to produce. Martensitic, centrifugally spun ductile, or the stainless. They're very similar to each other in thermal characteristics, temperature characteristics, durability characteristics. The biggest difference in why you see rings moving towards steels versus irons, whenever you do a steel ring, it's going to come out of a coil of wire. So I go out in the back, I've got big spools of wire. It gets, it's extruded into a near size. We coil it. I could literally take that ring. This is a steel ring. I could literally coil one ring if I wanted to coil one ring. Granted, I still got a day's worth of setup on it. I've still got to run, parts to make sure they're right. But I could literally coil one ring if I wanted to coil one. In iron, I have to have it founded. We're not a foundry. Like I said earlier, this is Phoenix, Arizona. It's hotter than heck in the summertime. The last thing I want to do is pour metal out back. So we have to have it founded. Well, if I'm having it founded, that's going to be a ring that's basically one bore size, very close on thickness, very close on radial, and I'm going to have to pour at least 500 pieces to get the foundry to even talk to me about pouring that material. Not 500 mix and match, one size, one part, 500. Then once I've got the castings, I can lap it, ID it, OD it, profile it, coat it, heat treat it. I can do all that, but I still have to have something to make it from. It doesn't come out of like a hunk of black water pipe. So I've got to have that material. So the shift in rings is to go into steel top ring, steel second ring, simply because I can make it from a wire and I can produce small runs, big runs. It's more cost effective, and I've got a better selection of material. So the hardened ductile iron, same thing. Our TNT, I have to have that founded. So I've got a limited selection of sizes. I only do it in very popular ring sizes, very popular bore sizes. Steel, I can literally do anywhere from about, oh gosh, we can go as small as about 2.5 inch up to about 5.25 inch on our steel stuff, and eventually we'll have more machines that will go beyond both those, we'll say limitations. But moving to steel, now that opens up my world into stainless steels, carbon steels, 9254 carbons, and into tool steels. And the whole point of each one of those is we go up that ladder, takes a higher amount of heat to heat treat. It takes more heat to get the part shape, to get it to that amount of open gap or free gap that we have in the ring. What amount of gap do I have determines the amount of tension I'm going to generate on that ring. The bigger the free gap, the more force it's going to take to close it. And we can adjust and modify that. But the base material has to be able to handle a certain amount of heat. So ways to tell what you need, and as I said, we've got the stainless, then you get into the carbons, then you get into the tools. Each one going up the ladder handles a greater amount of heat. So the question arises all the time, well, which one do I need? Well, we're going to talk about your application, what you're doing. Is this NA, is it turbo, blower, how much boost, what fuel? But one of the ways you can always tell on a ring, one of the things you want to do, and I'll bring it down here in black where you kind of see it a little bit. When you go, we're checking everything, we're blueprinting everything, we're file fitting everything, we're writing it all down in our build book. One of the things you always want to write down is what's the free gap on the ring? What is that number? Just laying on a table, what's that number? So when you disassemble that engine, this is one of the things you want to look at. You want to come back and remeasure that number. This number should be very close coming out as to what it was going in. You might lose 80 thousandths, maybe 100, but it should be very, very close. So just for easy math, if it goes in at 500, it comes out at 420. Hey, you're doing great. That material is holding up to your tune-up. But if it goes in at 500 and it comes out at 100, you got a problem. You've got heat, and it's collapsing the ring. The other thing to look at is tip alignment across the end gap of the ring. Those tips, when I close it down, they should always line up. They should never be like this. They should never be sunken down. So these are things, kind of that forensics, take as much time taking it apart as you did putting it together, because it's telling you a story if you're taking the time to look at it and listen to it. So that's kind of one of the things that will tell you what kind of ring material you need. Now, at the same time, if your tune-up's so out to lunch and it's so far off, I don't care what you put in it, you're going to nuke it. I can sell an M2 tool steel ring to somebody that's just killing parts. So all of this is said that you've got a good tune-up. It's not knocking the bearings out of it every run. You're not knocking the porcelain off the plugs every run. Everything looks good. Plugs look good, ports look good, everything looks good, but yet you're knocking the gap out of the ring. You simply need to move up the ladder in materials. Then we'll shift back to the coatings, So you've got the early days of like cast iron rings that had no coating. That ring's going to wear quick. Granted, it's soft, it's going to seat up fast, but it's going to wear quick. Then you're going to move up into, the coatings of chrome or moly. And one of the questions I like to ask people is, how many people put a chromoly ring in? And I always get this, no, you haven't. It's either chrome coated or moly coated. It's not both. They're not made out of 4130. We're not making it out of chromoly tubing. So the ring's either chrome coated or moly coated. So going way back, chrome was the first kind of an anti-friction that was put, coating put on a ring. But it is just that. It's an electrofusion plating process, just like taking your bumper from your Cadillac down to, the chrome place and having it chrome. It's a dip process. It's lumpy, bumpy, high spots, low spots. It's hard. The chrome of today is better than what it was 30, 40 years ago, 50 years ago. Everybody always complained about chrome rings not seating up, and they do a much better job today than they used to, but it's still hard chrome. So we moved into moly, plasma moly, molybdenum. Moly's your best friend and your worst enemy at the same time. Moly's very, very forgiving of different kinds of bore finishes. Molybdenum holds oil like a sponge. Rings ride on a film of oil, folks. They do not ride on the cylinder wall. The only time they ride on the cylinder is on a cold start or ring reversal, top and bottom dead center, when they stop moving. Think about a ring as like a water ski going across the lake. It gets up on plane on top and it rides on the top till we lose enough speed, just like when you're water skiing, that we sink back down. So think about it. You're sitting in the water, going to ski, you take off, you're plowing, you're in the water, then you come up on plane and you're on the top. Same thing with a piston ring. That's when a ring touches a wall. So we really don't want the ring to touch the cylinder wall, or we're going to get into wear problem. So molybdenum kind of gives you a little cushion there, lets you get away with cylinder finishes that maybe aren't quite perfect. Problem with moly is it doesn't stick very well. So it doesn't like to go on real thin rings. There's not enough area to keep the moly attached. And it doesn't like detonation. It doesn't like big boost. It doesn't like a nasty environment. So it's okay in OE stuff, but you start getting into power adders, nitrous turbos, blowers, it'll launch the moly out of the ring. The moly's fairly hard, gets stuck in the skirt, returns the favor, tears the heck out of the cylinder wall. Everything goes to heck in a handbasket. So in today's world, we really don't use moly much unless it's a relatively basic application. Today's world, we use what are called PVD coatings, physical vapor deposition. These are applied in a vacuum chamber. This particular ring has a chrome nitride face coating on it, CRN. It's a silver coating. This coating goes on, it wears very well. It's very smooth. It mirrors the substrate very well. It's not lumpy, it's bumpy. If we make the base underneath perfect, the coating's going to be perfect. It mirrors that surface. Will lay between 3 and 6 microns thick, depending on if it's a single layer, double layer. But it's a relatively hard coating, but it seats up very well and it lasts a long time. This is part of why modern rings do so well. You've got hard coatings, they last a lot longer. So moving up that ladder, depending on your application, we have tungsten carbide carbons. It's a black coating. It's actually a little softer than this. And we move into titanium coatings, tinitride, like a drill bit would be coated with. Very hard coating, lasts a really long time. And then new exotics like diamond like carbon, DLC, same kind of stuff you put on a wristband. So depending on what your application is, what you're doing, we offer different materials and different coatings. And we love your questions. We love the phone call. We love the email. Hey, everybody asks us, what's the best thing for us to do? I can give you basic parameters, but when I know a little bit more about what you're doing, this application, this fuel, this kind of block, here's what I expect out of it. I want to get, like an NASCAR. I need to get 1,500 miles out of the bottom end. Or, V8 supercar down in Australia, I got to get 3,000 kilometers. Well, I'm not going to put a plasma moly ring in because it's not going to do that. So when we know more about what you're doing, we can definitely guide you down that correct path.
Great. That was a lot of information. I appreciate that.
Sorry, I didn't mean to get rambling, but I get going. And hey, I think I did all that on one breath.
No, that's good. It's good information. I know you're a busy man. I only have the
I got all day, man. I'm here till 5 o'clock. So hey,
I only have the regular version of Zoom, so it's telling me in 2 minutes we're going to get cut off whether we like it or not. And so,
well, we've hit number 9. What are the biggest mistakes? A couple things that you asked me. What's our latest thing? One of the newest things we're doing is gas port and piston rings. I'll try to make this quick. Anytime we get into high cylinder pressure boosted, we've got to have a gas port, folks. It just needs to be there. So if you're buying an LS stroker kit, you're going to put a 30-pound of boost turbo on it. You buy a shelf piston. There's no gas ports in the piston. You need gas ports. We can put the gas port in the ring. It does a much better job. It's rotating. It's turning. We don't get high pressure contact points in the bore. When we have fixed gas ports, we don't get carbon buildup in the ports. So the gas ported ring is basically a better execution of a great idea. So this is the perfect thing for guys that are buying kit pistons, or didn't realize, oh, hey, I built it NA. Now I'm going to boost it. It's got to go. So that's a big thing. Biggest mistakes guys make at home. Use proper ring compressors. Don't beat pistons into the engine. If it doesn't go in, stop. Something's catching. Monday morning is I'll call a palooza of broken parts by the weekend home users, busting stuff because they're pounding them in. Stop. If it doesn't slide right in, stop. Chamfer on the floor. Something's going on. Other thing is, make sure you get the cylinders hung correctly. We're not doing lawnmowers here, folks. We're doing racing engines, performance engines. You want to go to a professional machine shop, get the cylinders done correctly. Barry Bush on a hand hone, I mean, that'll get you by at the racetrack to get you through a couple passes. But if you're building an engine, make sure you're having it done by a professional when it comes to honing the cylinders.
Great. And
no synthetic oils when you break it in. And you don't need to add chemistry to a good oil. Don't buy somebody's add-on oil additive kit. Buy the good break-in oil, use it, be happy.
All right. Well, we want to say thank you very much, Keith, for coming on and letting us know about all the things that you talked about. That was a good deal of information, and I appreciate that very much. Possibly we can have some of our viewers to ask some questions, and maybe we can have a follow-up video with you answering those. Keith has been a wealth of information for me. At more than several times, I have emailed Keith and bounced some stuff off of him, and even on this 496 forced induction build, I sent Keith an email and asked, "Hey, where would you set the end gaps on this?" So, just a wealth of information. Glad he's there, and I appreciate him being on the channel. If you guys haven't taken the time to subscribe to the channel yet, I would urge you to do that. I plan to have many more interviews like this from different industry professionals, and we got lots of cool engine builds coming up too. All right, hope you guys are having a good weekend. See you soon.